we're going to look at projectiles at an angle again, but we're going to do a little bit more math. Now, this section is not going to have as much math as the horizontal projectiles because we're just worried about what happens with the velocities, which then we look at conceptually what happens in terms of height and range. So just a reminder about what we learned in terms of concept for our angled projectiles. First is that the Vx is constant. So that's your theme you're going to see all the time with projectiles, is Vx is considered constant. It doesn't change. The Vy is going to follow the same pattern as throwing in the air, which means your initial velocity is not zero. Okay, initial velocity is not zero. The Vy, which is the vertical, decreases going up, 0 at the top, and then increases going down. And actually, if you want to put an extra little square here, we also said that the final, when it hits the ground, equals the negative of the initial, so at ground. And Vx is constant, which means Vx will always be the same number, and we'll see how that plays into these examples that we do. So just looking at this diagram again, it's the same one that you saw in the previous video. Your green arrows are your horizontal. They all stay the same length. The verticals decrease in length going up until they hit 0 at the top, and then increase on the way back down. That's why the overall resultant changes so much. The resultant changes because of the vertical. So here's an example. This example should look really, really familiar because we did a lot of them that look like this with vectors. So it says a ball is thrown in the air with an initial velocity of 8 meters per second at a 30-degree angle. What are the initial horizontal and vertical velocities? Well, we're given an amount for the initial velocity. That's your resultant initial velocity. We're looking for the horizontal and vertical components, which means triangle. Remember, we always draw them in the same orientation. The angle always goes at the bottom with the 90 degrees, and our number here, unless specifically stated, is always going to be the hypotenuse. So now we need to find these different colors. V initial in the vertical, so V naught Y, that's a Y, and V naught X, but remember they're all the same because Vx is constant, so just Vx. So V naught Y and Vx. So let's find V naught Y first. So this is the opposite side from the angle, so it's opposite and hypotenuse, which is sine. So we'll do sine of 30 equals opposite, which is V naught Y, over hypotenuse, which is 8. So to solve for V naught Y, we're going to multiply by 8 on both sides. Cancels out over here. And so we get 8 times sine of 30. Make sure your calculator is in degrees, and you should get an answer of 4 meters per second. So it'll have a vertical initial velocity of 4 meters per second. So now to solve for Vx, there's 2 ways you can do it. One is, now that you have 2 sides, you can use Pythagorean theorem to solve for this one, or you can just use another function. So I'm just going to use another function. This is adjacent to the 30-degree angle, so it's adjacent, and hypotenuse, which is cosine, so ca. And so we'll set it up exactly the same way. I'm just going to skip one step. So Vx equals 8 times cosine of 30. So Vx will be 6.928. So now let's talk about what these numbers mean. Notice with a smaller angle than 45, your V naught Y, your vertical velocity, is smaller than your horizontal. So 4 is less than almost 7. So the smaller the angle is, the smaller this vertical velocity will be. That'll come into play a little bit later. So now let's talk about what happens at the top of the path. So I'm going to use my same colors. So Vx is going to be blue and Vy is going to be red. So we said that the horizontal is constant. It doesn't matter where you are, the horizontal will always be the same. So at the top of the path, the horizontal velocity is still going to be 6.928 meters per second. It is not 0 because it's constant. So the horizontal is 6.928. The vertical, we said it decreases going up. It's 0 at the top and then increases on the way back down. We're right here where our Vy is 0. So Vy is 0 at the top. So horizontal, vertical. So what is the resultant? Well, to prove it to you that the resultant, which is the overall, to prove that the resultant is the horizontal, let's plug it into Pythagorean theorem. A squared plus b squared equals c squared. So our a squared is our horizontal, let's just say. So 6.928 squared plus b squared, which is 0, equals c squared. And so 0 squared is 0, right? So this goes away. So we get 6.928 squared equals c squared. Now, I don't actually have to solve this for square because what I'm going to do is square it and then take the square root. So what's the square root of this squared? Well, it's the same thing. 6.928 meters per second equals c squared. Or, sorry, equals c. So our resultant velocity is the same as the horizontal. And that's for the top of the path. That's the most important part. The resultant is the horizontal at the top of the path. So now let's see what happens whenever it hits the ground. So whenever it hits the ground, we're going to have a triangle now, right? Because we have a vertical component and we have a horizontal component. The vertical component, we said when it returns to the ground, make sure I use my right colors. So when it returns to the ground, our Vy is equal to the negative of our initial in the vertical. So our initial V naught y was 4. So Vy is going to equal negative 4 meters per second. The horizontal is constant. It doesn't change. So the horizontal will still be 6.928 meters per second. So Vy is negative 4, Vx is 6.928. So if we were to draw this on a triangle, so here we go. Again, drawing them in the same orientation. The horizontal is going this way at 6.928 meters per second. The vertical is going down this way at 4 meters per second. You should notice these are exactly the same two sides. So to prove it to you, I'll show you again. So here we go. The vertical was 4. The horizontal was 6.928. 4 and 6.928. So you can plug this into Pythagorean theorem to find this side, and what you're going to notice is that it is the same as the very initial. So the final equals the negative of the initial. So this would be negative 8. So it would be going in this direction. So now let's just kind of look at how these velocities are different and then how this changes our range. So if we were to use the same numbers, so 8 is here, so this was our triangle, right, with 30 degrees. 8 was here, this was 4, and this was 6.928. If we were to do its complement, so 30 degrees' complement is 60, then all that would happen is these two sides would switch. This is still 8 because it's the hypotenuse, but now across from the 60, just here, across from the 60 would be 6.928. And across from the 30 would be 4. So what you see is that with complementary angles, you get the exact same sides. The difference is which one's vertical and which one's horizontal. So if we were to look at these in terms of what their paths would look like, this one, let's see, let's use a different color. This one would go up and then back down. This one would go outward more and come back down. So see how there's a larger vertical velocity, which means it goes higher. A smaller vertical velocity means it goes lower. So that's why the heights are different. The xy components, whichever one is on the correct side, determines which height goes with it. So higher goes with the larger angle because there's more velocity. The range stays the same. Here to here is the same as here to here. So the components tell you how the heights differ, but for complementary angles, the range is the same.